The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI Conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI Conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
Second presentation will be made by Lev Khazanovich from the University of Minnesota, and he will give us a summary of pavement design, rigid pavement design, from the past to what is upcoming here in the future.
Thank you, Pete. It's a great pleasure to present here today, and I recognize that my topic is a little bit ambitious for a 20 minutes talk. When in a minute of weakness I agreed to make this presentation, I didn't recognize that it will be so short. So I decided to focus on one topic, which probably is appropriate for the ACI convention, is a need for better concrete characterization for pavement design. But to really justify it, we need to go back and see how concrete pavement design was involved, what we have now, and what do we need to do in the future. Well, as probably everybody here in the audience know, that the rational concrete pavement design started from a pioneer in Westergaard work in 1926, and he proposed to treat concrete pavements as plate resting on winker foundation. And basically, this requires to characterize concrete slab using Young's modulus, Poisson's ratio, standard elastic properties, and concrete slab thickness. And this model has been used in many design procedures, and it's still used in the current mechanistic empirical pavement design guide, and generally speaking works exceptionally well. And all the attempt to deviate from this were not extremely successful so far. So Westergaard also obtained 3 very important closed form solutions for interior, edge, and corner loading. And he found that the maximum deflections occur at the corner and the corner loading, and maximum stresses occur at the edge loading at the bottom of the slab. And because of that, for quite a while we believed that cracks always initiate from the bottom and propagate to the top. Now, going back to material characterization, we had only a few parameters, mainly Young's modulus, but in this case it works in opposite direction. If you increase Young's modulus, your stresses in the concrete slab will increase, but on the other hand, the deflections will decrease. So that creates 2 opposite trends, and it's much easier just to play with concrete strength if you want to prevent cracking, so increase concrete strength or increase concrete thickness. So that's for a long time the best way to improve concrete pavement's performance was believed to be just increase thickness or increase strength. Westergaard also developed solution for slab curling, and that required characterized concrete with a coefficient of thermal expansion, but curling hasn't been used in design for quite a while, and even the currently promoted by the ACPA street pave doesn't consider built-in curling. Maybe I don't know the latest model, the latest version, but I believe up until recently curling was not considered. Westergaard himself recognized that his theory has quite a few limitations. He considered only single slab and no joints, infinite or semi-infinite slabs in horizontal directions, which means no slab size effect. He didn't analyze the effect of base layers. He ignored separation of slab from the subgrade. Consider only single wheel load. So all these assumptions were recognized since Westergaard's time, and he himself tried to resolve some of them, especially single slab problem. And there was significant research for quite a while after that aimed to address those limitations. But only after the introduction of the finite element method, it became possible to address all these limitations completely. And there are several finite element programs which we developed specifically for analysis of concrete pavements. I just mentioned a few of them: Ken slab, J slab, every fee. But the most popular, the finite element program was ILE slab, and there were several versions of this program which addressed various limitations of the Westergaard theory step by step, and eventually that program was replaced with a computer program iSlab 2000, which was used in the development of the latest mechanistic empirical pavement design guide. So by the end of 1990s, we believe that all major limitations of the Westergaard theory are addressed, and basically what needs to be is just to implement it into design completely. But at that time, actually, the design mostly was done using empirical AASHTO equations, which again characterize concrete using modulus of elasticity and flexural strength. That's it. Well, again, it's a pure empirical equation. Basically, even these parameters are indexes and cannot be really improved. And it caused very thick pavements for high traffic on the interstate highway. So this is why the AASHTO and NCHRP decided to develop a mechanistic empirical design guide. And I was privileged to be a member of the development team, along with several speakers from the session today. And when we started working on the NCHRP 137A project, we believe that what we need just to take Westergaard theory, calibrate predicted stresses with field data, and that would do the work, the job. But there was one event which actually messed up everything, and that was a failure of the interstate highway I-80 in Pennsylvania. When they reconstructed the section I-80, they decided to play safe. They built 13-inch thick slab. The design life was 40 years, but in a couple of years, transverse crack started developing. Of course, the first reaction was either thickness deficient or strength deficient. Nope, everything was fine. What was even more difficult to explain, why that section failed and adjacent sections, which are much thinner, perform reasonably well. What made it even more complicated was that forensic study indicated that cracking initiated from the top and propagated it to the bottom, which completely contradicted the Westergaard theory. And the number of cracks kept increasing, which means it's not just shrinkage, plastic shrinkage cracking, it's structural cracks, and kept developing. So at that time, PennDOT issued a moratorium on construction of concrete pavements, and Harris Consultants, which I was a part of, which at that time was asked to investigate that failure. At that time, we just finished development of iSlab 2000, and we decided to simulate various loading conditions. And again, as always, it's easy to explain 50% of the data. We could either explain why this pavement failed, but we couldn't this time explain why the adjacent slabs didn't fail. But what the most difficult part was explaining why it's cracked from the top. And we had to eliminate another implicit assumption of the Westergaard theory. It's built-in curl. So basically, Westergaard assumed that there is no temperature gradient is acting on the pavement, then the slab should be flat. But in reality, due to reversible shrinkage, and due to non-uniform temperature hydration, the corners of the slab always curl up. And that effect was not completely unknown. It was reported by Chilean engineers, and before that it was theoretically explained by Eisman and Lykov from Technical University of Munich, and actually we even used it in one of the research studies, but never been used in actual evaluation design practices. So, but as soon as we incorporated this shape, we managed to predict that top surface stresses are higher than the bottom stresses, and actually those stresses can be significant enough to cause cracking. So that was, I believe, in 1998, 1999, and that finding was significant enough, so we decided that it's very important to incorporate that mode of failure into the MEP, Mechanistic Empirical Pavement Design Guide, and the built-in curling must be a part of the design guide. So and that was done, and that brings us to where we are now, Mechanistic Empirical Design Guide. So again, I'm not going to discuss it in detail, so basically we're predicting stresses and deflections using Westergaard theory, and we incorporate built-in curl. But built-in curl here is an input parameter which was determined through field calibration. So it's a certain index which allows us to match predicted and measured cracking. It's not predicted rationally, and it may, for example, it may not work for certain regions or for certain construction practices. So it's a major limitation, one of them. So that brings us, and well, this design guide is still under implementation. Some states already implemented it, some are still implementing. But I believe it's a good time to start talking about what needs to be done in the future. And I prepared just a very short list of limitations or deficiencies of the guide. And not because it's incomplete, but that's because, well, those 5 topics excite me the most. Well, the current design guide doesn't incorporate longitudinal cracking, which might be an issue, because, especially for states like Minnesota. If you start building widened slabs, then design guide allows you to design to be very thin, and of course, the design guide correctly predicts that those pavements will not fail in transverse cracking. They will fail in longitudinal cracking, which might be even worse. But currently, the design guide doesn't have this model. I don't have time to talk about reliability analysis, but that's a big issue. And one of the main deficiencies of the design guide is it does not correlate variability of inputs with variabilities of the outputs. The reliability analysis is based only on correlation between predicted and measured distresses, so it does not permit related to construction practices. And I'll briefly talk about some other limitations later. But probably the most significant limitation of the design guide is that it's a rehabilitation part. The design guide, generally speaking, does a reasonably good job in predicting performance of newly constructed pavements. But these days, new construction is a relatively small part of construction activities. Rehab takes most of the efforts. And the performance prediction models in the MEPDG are really over simplistic. Let's just consider one example, an unbundled concrete overlay. And it's, well, all of you know that it's a way to rehabilitate concrete pavement in a poor condition by placing an interlayer and placing an overlay on top of it. And although the interlayer is supposed to separate the existing pavements and cracks in the existing pavements from the overlay, but still a reflection cracking is a major concern. Partially because if you try to simulate this system in Abacus or in the latest version of iSlab, for example, it always predicts very high stresses above the crack if you place the load on top of it. And we understand that most likely the stresses are fictitious, they are not realistic, but still they have to be accounted for. Generally speaking, this rehabilitation option performs exceptionally well, and that's why many people believe that we're over-designing these overlays, But unfortunately, mechanistic-based models are even more conservative than empirical one. So to investigate this issue, Mindat decided to build couple test sections. Maybe Tom will talk about them later. And one of them was 4-inch thick overlay over 7-inch thick existing pavements. And all mechanistic models and empirical models predict that it's too thin overlay and it should fail pretty soon, and it actually did fail. But it's very important to note that the mechanistic model predicted that the thickness overlay is not enough to resist reflective cracking. So an overlay failed approximately in 2 years, give or take. But if you look at these cracks, transverse cracks, they are not reflective. And forensics shows that they are not located on top of the cracks or joints in the existing pavements. And moreover, you probably can even observe from this plot, majority of them are top down. But if you try to predict stresses in this location, just using Westergaard theory or using the current models which are implemented in the mechanistic empirical pavement design guide, which incorporates built-in curl, but it assumes that the overlay does not separate from the existing pavement, you will not get any stresses here, and you always get very high stresses at the bottom stop, and it's difficult to predict any significant stresses away from the slab. For example, even more difficult to predict crack propagation here. So we decided to conduct very simple finite element simulation. So we used iSlab 2000, and we modeled an overlay as using plate elements. We use an interlayer. For interlayer, we use spring layer, the Totsky model, and another plate layer for the existing pavements. And you see many joints here, but some of them are just, it's the way how iSlab models them. Some of them are rigid, so which basically there is no joints. It allows to model mismatching joints. And the results was mixed. So on the one hand, after we incorporated a significant built-in curl, so now it's built-in curl in the overlay only, we managed to predict quite significant stresses on the top of the concrete pavement. But on the other hand, when we placed, I don't have the slide, but when we placed our load here, we still had very significant stresses at the bottom of the overlay, and those stresses were higher than actually top stresses this location. So we kind of solved 50% of the problem. We can explain why the crack occurred from the top, but we couldn't explain why reflective cracking did not propagate. Fortunately, we were recently awarded a study, and we hope to resolve some of these issues, at least in the next few years. But what is absolutely clear, that to really develop a rational rational model for analysis of unbounded overlays, we have to predict built-in curl correctly. It shouldn't be just an index for calibration. It must be done on a rational basis. It's number one. And second, we should be able to characterize strength on the overlay not just by modulus of rupture, but using more sophisticated fracture mechanics based approach, which again it will be subject of another presentation. Now, so basically, everybody understands that built-in curl is a very important parameter. At least all researchers understand it. The only question why it's not done yet, because it's extremely complex phenomena. So we have to account for variety of parameters like effect of construction, ambient humidity, solar radiation, wind, and so on. We have to account for cement of hydration, because a portion of built-in curl comes just from non-uniformity of cement hydration immediately after concrete placement. On the other hand, we have to account for concrete creep, and it's very difficult to find concrete creep data at early ages. People start measuring them or modeling them like after 7 days, like 3 days at most. But when we go into really early age, the amount of available data models is really limited. well, shrinkage, here we have a little bit more data, but still everything should be focused on early age. And finally, concrete fracture should be reconsidered, again, especially at early age, because now the time at which joints are formed will affect our built-in curl, well, initial construction shape. And just to add it, we recently completed another study when we shown that this built-in curl is not only affects the mode of failing, it not only affects stresses and deflections, but it also a major contributor to roughness. So basically, it's extremely important parameter, and that's where a major efforts in future research has to be done. It's quite possible that individual researchers are working on this topic here and there, but as far as I know, there is no major concern efforts to really combine this concrete material modeling with pavement design, because in the past the similar models were developed by like Hyperpave, but they concentrated on joint formation. We need to concentrate on complete pavement modeling and prediction of deflection shape. So, how am I doing on time? Okay, just one slide. So basically, just I hope I made the case that characterizing concrete, just using modulus of elasticity and coefficient thermal expansion and modulus of rupture is not the way to go for the advanced design procedures of the future. So we must significantly improve our material characterization. And another very important notion that we need not only be able to predict it, but we should be able to control it during construction practice, and everything is now controlled. So built-in curls should be predicted and should be controlled in construction. So that's what the message you can take home today. Okay, so that concludes my presentation. I will be happy to answer any questions you might have. Yes, please.
So the ultimate solution then is really in the construction procedure problem itself. The ability to analyze the stresses and predict the cracks is one thing, but really it's too late at that point. You want to try to predict before you start with, right?
Absolutely. Well, I repeat the question. The question is, it's we need to make efforts on the construction process, not on the design process, because at that time it's too late. Absolutely, but the question is, to really improve our construction practices, we should have a better understanding what's actually what the effect of built-in curling, and develop procedure parameters and to understand parameters which we must control during construction. So because currently just random you can have several test sections with similar design. Actually, it's SPS2 in Ohio. Very minor difference in design. One of them was constructed I believe, in spring, another in fall. Totally different performance. So, and actually, probably the same contractor was built.